Hello, everyone, and thank you for coming to my talk. My name is Arun Kumar. I'm an assistant professor of computer science and data science at the University of California, San Diego. It's a pleasure to be here at KDD, the Applied Data Science Talk Series. This is my first time at KDD, so thank you for having me over. I'd like to share some thoughts on what I call the new DBfication of the world of machine learning and AI, and how I think the data mining community and the database community need to reignite their Nexus as part of this. Now, it's no secret we are all living in the golden age of ML and AI. All the major tech companies, the big web companies, they are using ML extensively for all sorts of products. This has led to an enormous demand in the various enterprise sectors, healthcare, finance, insurance, retail, telecom, and also in the academic domains in various sciences for tools that make it easier for them to adopt ML and AI into their data analytics applications. The International Data Corporation, which is a market research firm that studies data software, estimates that the market size for products that make it easier to adopt machine learning is set to grow to almost $500 billion in the next few years. That's an astoundingly large figure, but that's what the IDC estimates. Naturally, there's an enormous amount of activity in this space. There's a slew of open source tools that have become very popular. All the major cloud giants are also going after this space and building a lot of ML AI services. In spite of all this progress, as I'll explain today, there still remain numerous fundamental efficiency and usability bottlenecks in the end-to-end process of building and deploying machine learning applications. At the end of the day, that's what my research is about: devising new software abstractions, algorithms, and building software systems to help democratize machine learning-based data analytics by mitigating those sorts of bottlenecks from a data management and systems standpoint. By democratization, I mean precisely the following: improve the system efficiency, so reduce the runtimes and the resource costs of the tools involved, and improve the human efficiency, which is improving the productivity of the people involved in the loop. It requires unifying and synthesizing these worlds of not just ML and AI, but also data management and database techniques, and straddling the whole system stack. More concretely, I build practical and scalable data systems for ML and AI analytics. These are inspired by the principles of relational database systems that we've been studying for almost half a century now. I also exploit insights from computational and statistical learning theory and optimization theory, which are at the root of what ML computations are about. I have interacted with data practitioners, data scientists, ML engineers, data analysts, business analysts, domain scientists in over 36 settings across enterprise, web, healthcare, and academia to understand this end-to-end picture of the ML lifecycle. Based on my conversations, I kind of call out three major stages: source, build, and deploy. In the source stage, they convert raw data, such as multi-table relational databases, text corpora, multimedia, time series, and so on, into data sets that are ready for ML to be applied. In the build stage, they convert those ML-ready data sets into precise prediction functions or pipelines, where the process of feature engineering, algorithm selection, hyperparameter tuning, collectively called model selection, takes place. And once they have this prediction pipeline, they need to integrate it, deploy it into their application. This could be as simple as integrating it with your data warehouse for business analytics, or plugging it into an online cloud-native service for people to access from around the world. This lifecycle is not just a one-shot. You have to monitor and maintain the ML models as the application evolves, as the data evolves, and keep the models fresh. And across this lifecycle, the data scientists and ML engineers use data systems and ML systems for achieving all these tasks. In this context, my research approach is the following. Based on my conversations and understanding of this whole lifecycle, I abstract key data-intensive steps in this process. In this lifecycle, formalize the computations, both from a data flow standpoint and from a semantic standpoint. That allows me to automate a lot of the grunt work that takes place manually today. And once we have formalized the computation, we can now bring to bear systems and database techniques to optimize their execution and improve the system efficiency as well. So that link down there is my research group web page, where I lay out the various projects that tackle different parts of this life cycle. But for today's talk, what I want to highlight is the connection between the data mining world and the database world, and how I believe the data mining world can play a key role in what I see as this new DBfication of the ML world. In the DBfication part, I'm going to give two concrete examples from my own research, but these are exemplars for this whole DBfication that is a larger thing that has happened. One is on scalable deep learning systems, where I look at how system efficiency can be improved. And the other one is on automating data preparation steps in machine learning in so-called automated machine learning platforms. Okay, so let's start with this. All of these names must be familiar to you all. They are the original kind of gang of data mining stalwarts, people who created this field of data mining. All of them are from the database community. You can see some of their early publications actually forked off data mining as a field. All four of them have the KDD Innovations Award. And I think some of them also have the Sigma Innovations Award. So the roots of the data mining community really is in the database world alongside the ML and AI worlds. But a part of me is wondering, in the last decade, data mining has come to be called as just applied ML. And I wonder, when did that happen? Why did that change happen? What happened to the original dream of the data mining area as being about making machine learning practical for regular users? What do I mean by practical concerns? So in the machine learning world, some of the common concerns are accuracy overridingly. Of course, you want to worry about prediction accuracy, but sometimes you also worry about runtime efficiency. But in the systems world of machine learning, there are additional practical concerns. One common concern is, what if your data set is too large to fit on your single machine memory? That is a concern of scalability. And you also want your algorithms and your systems to be efficient at scale. In ML, you need to configure features. You need to engineer features, extract features. You need to configure models, as model selection. And a lot of that is there are usability challenges. In production settings, especially in today's web companies and IoT world, you have to fit these sorts of workflows into production systems in a seamless manner without disrupting their workflows. That is the concern of manageability. And people who are building these software tools need to build them quickly and seamlessly. It should not be a very tedious chore. So that is the concern of developability. Now, all of these concerns have been studied intensively in the database systems world in the context of relational and SQL computations for almost half a century now. In the ML systems world, we need to study these concerns as well. And one key differentiator in the ML world is that sometimes you can trade off a little bit of accuracy to gain enormously on any one or more of these practical concerns as well. So there is something interesting in the departure there as well. Given that background, let me now explain what I mean by DBfication of ML and AI. In the last few years, people have realized that just the ML algorithm or just the code, that the Python scripts that you write for ML, it's a very tiny part of this whole infrastructure that is needed around ML. Everything from data collection and validation, to extraction, to process management, to model serving, all of that requires infrastructure. This diagram is from this famous paper from Google, Hidden Technical Debt in ML Systems. And so this push to platformize ML and AI has been taking place. And when I look at it, I always think of, well, platformization has been happening for 4 decades now. Back in the 80s, SAS was the original king of enterprise ML. And so since then, we have been trying to platformize ML with various sorts of systems. In the mid-90s, the R programming environment took off. In the late 90s to the early to mid-2000s, which is when the data mining community also started to fork, you had, in the database world, in RDBMS, machine learning systems, basically bringing ML algorithms to database systems like SQL Server, Oracle, IBM DB2, and so on. And these companies built these tools that scale ML algorithms to database resident data. Some of these tools are still around. Oracle data mining is still being used by many Oracle customers. So they allow you to platformize ML by integrating it into your enterprise applications in the database itself. Later, in the late 2000s, when the so-called big data revolution took off, data flow systems started to come about. People also realized that scaling individual ML algorithms is very tedious. So as the complexity of ML started to grow, people wanted better system abstractions for scaling out ML. And so these tools like Apache Mahout on MapReduce and Hadoop, Spark MLlib, Parameter Server, MADlib on Postgres and Greenplum and GraphLab, all of these started to come about in trying to build better systems infrastructure for ML. In the last half a decade, there's been an explosion of activity in this space. In the mid-2010s, we had this growth in tree learning systems and deep learning systems. Boosted trees, tree ensembles, XGBoost and LightGBM are very popular on structured data. TensorFlow, PyTorch, these sorts of deep learning tools are very popular on unstructured data. And in the very last few years, there's been a larger platformization effort from the cloud giants. ML/AI services such as SageMaker and Google and others have their own. And then in the platformization, TensorFlow extended, tools like MLflow, these all came about to look at the entire life cycle of ML. And then there's also these new development with feature stores. The way I see it, this sort of rise of the systems and platforms for ML today resembles the rise of relational database management systems circa 1980s, where people took relational and SQL computations and built this whole infrastructure around them to democratize them. That is what I call the new DBfication of ML/AI. Across this entire life cycle, there's data management and systems challenges that need to be tackled. For example, in the sourcing stage, we need to handle metadata management for ML. Where do the features come from? Where do the data sources come from? Who's using what? We need to do data preparation and cleaning. These are human-intensive work that still requires a lot of pipeline construction. Multimodal query models are needed. We need to fuse signals from various data modalities. Data search systems on data lakes, labeling systems, all of these are needed to help democratize ML. On the build and deploy stages, we need to build scalable data systems for ML, systems that can seamlessly scale across not just single node disk, multi-node disk, cloud native environments, streaming and serverless, all of that. And once we do this sort of scalable execution, we want to make sure they are utilizing the resources efficiently. Their query optimization techniques matter, just like it mattered in the context of SQL and relational algebra. And given this whole pipeline that often straddles multiple tools and multiple languages, provenance is important. You need governance, you need debuggability to improve the pipelines when errors happen, when failures happen. How do we improve these sorts of pipelines? So these are all data questions. These are all questions at the intersection of data management and ML that need more attention. And overarching across the lifecycle, we do not just need to build these sorts of new tools. We also need to understand their phenomena, their properties. We need to benchmark these sorts of tools and frameworks for their efficiency, for their accuracy. We need new label data sets that can allow you to compare tools, which one is better than the other. And of course, benchmark data sets have also revolutionized the AI field, stuff like ImageNet. We need some of that for things like data preparation as well. And there are these overarching concerns of privacy, security, fairness, transparency, accountability, and so on that still matter in this overall context. In my own work, I have looked at three main groups of work. I looked at metadata management, data preparation, and multimodal ML query models. I've also built systems, scalable systems for ML, and devised numerous query optimization techniques. And I've done a lot of benchmarking of systems and also created benchmark data sets for the ML platforms. And in today's talk, I'm going to highlight two of those pieces of work from my recent research, starting with one on scalable deep learning systems. Okay, now imagine you're a data scientist who's building a deep learning model on large amounts of data. How are you going to go about it? So today you would use your tool like PyTorch and TensorFlow, specify your neural computational graph, and then run it on your cluster. Maybe it's managed with Kubernetes or some cluster manager. You have GPUs, CPUs, memory, disks. But there's a major issue here. Model building in deep learning is never one and done. You need to run model selection. It is inevitable because of the bias variance noise trade-off. You need to tune data representations, neural architectures, hyperparameters, and so on. And so this model selection process needs to be run efficiently at scale. That's the view we take in Project Cerebro. The data scientist is asked to specify the model selection process holistically, more holistically at a higher level, using APIs such as Keras or others for things like hyperparameter tuning and architecture selection and ablation studies and so on. They can still use PyTorch and TensorFlow for specifying neural computational graphs and stochastic gradient algorithms. But under the hood, Cerebro acts as an intermediary, which will translate their specifications into more optimized executions on the cluster. And here, by optimizations, I mean the database style multi-query optimizations for deep learning systems. This is sort of the first of its kind in kind of the deep learning world. This sort of decoupling of the what of the execution from the how of the execution is classic database style system design. This is what we did for relational algebra and we are doing that for deep learning systems. This sort of decoupling, this logical physical decoupling, also allows us portability. With the same specifications, we could now execute the same workloads across any environment. You could run it on a Spark cluster if you have it. We have kind of integrated Cerebro with Spark. You could run it in a cloud native fashion as well on just basic infrastructure as a service. So we published about this vision of Cerebro at this database conference, CIDR, earlier this year, and that's the vision paper that I refer you to as a starting point. Let me briefly explain this full vision of the Cerebro platform. It's a layered platform. There's 3 layers. The topmost is the user-facing model building APIs layer. All your favorite model building APIs, from hyperparameter search to architecture search to transfer learning, ablation, building multiple models over separate groups, sequence analysis, graph analysis. We will overload existing popular APIs, such as in Keras, and that'll allow you to specify your model selection tasks. You could use your standard Jupyter notebooks as you do, or command line interfaces. We're also building an interactive kind of graphical user interface for Cerebro as well. At the lowest level, we have the infrastructure, the execution and storage layer, where the data sets reside and the computation hardware reside. You could directly access the file system, or if you have a data flow engine, Cerebro is going to be integrated. It's already integrated with Spark. It's integrated with Greenplum, parallel BMS from VMware. And we're also going to make it available in a cloud native fashion, where you could use infrastructure as a service directly. The secret sauce of Cerebro lies in the middle, the optimization and scheduling layer, where we translate the what of the specification to an optimized how of the execution. And here we are devising a suite of novel hybrid parallelism techniques. One of the techniques we recently published is model hopper parallelism for deep learning model selection at scale. We're also devising new hybrids. More papers are coming out at VLTP and Sigma and other conferences this year, and they'll be coming out next year as well. We're also building memory management and virtualization capabilities for transformations of data in this context. So it's starting to look like an RDBMS, right? One thing to note is in all of this, we are building them around the deep learning tools that are popular today, like TensorFlow and PyTorch. So for things like specifying the computational graphs, AutoDiff, SGD updates, we're reusing existing TensorFlow and PyTorch assets without modifying the internal code. So these are all just wrappers around these existing toolkits. They'll be backward compatible. So as these compilers and hardware architectures of these deep learning environments evolve, Cerebro will be able to automatically leverage them in the future as well. On the side, we are also helping manage metadata using standard tools that are popular these days, MLflow, using TensorBoard for visualization of results. And there will be an explanation engine for understanding the prediction results. And all of this will be natively fault tolerant and elastic, especially in the cloud setting. To summarize, Cerebro is the first model selection first platform. It's a layered data platform for large scale deep learning. And we are really targeting scalability along all axes, data, model, tasks, and so on. It allows you to specify your workload at a high level, and it infuses novel multi-query optimization techniques. Together, we can get much better resource efficiency than all prior art, and it allows for better productivity of deep learning users because they can focus on their analysis tasks rather than worrying about systems issues. Now, I'm happy to say that Cerebro is already being used and practiced by our collaborators in the public health field here at UC San Diego on terabytes of labeled time series data from accelerometers to understand people's exercise activities. We are also planning to collaborate with computational physicists and materials engineers to apply parts of systems to their tasks. It has been shipped by Apache MadLib, which is an open source library for RDBMS ML, by Pivotal, and VMware is also collaborating with us to kind of put these sorts of ideas in front of their enterprise customers. We have open sourced all of our Cerebro related software, including the integration with Spark, which we presented at the Spark AI Summit. More workloads, more optimizations, and more use cases in various domain sciences are in the works. So I'd like to thank all these agencies for their generous support of this project. You can see really a diversity of agencies from healthcare to basic science to industry as well. Okay, so that was on the kind of systemsy aspects of ML. Well, let's look at a second example from our research, data preparation. Now, in the last few years, automated ML or auto ML platforms have exploded. Transmogrify from Salesforce Einstein, SageMaker from AWS, TensorFlow Extended from Google, they all claim that they have now automated data preparation, which is like this, it used to be a very data, kind of human intensive step. They say they can automatically transform the data from your raw tables to ready it for ML. And that involves things like identifying the schema, identifying feature transformations, and so on. When we looked at this, one basic question we saw was, no one knows how good these automated data prep steps are, objectively speaking. So that's what we set about trying to answer in Project Sorting Hat. We wanted benchmarks for machine learning data prep. What are the components of a benchmark? We saw three main things that are needed. We need to formalize the task definition. Right now, people are doing all sorts of things on their own. It's like the Wild West, to each their own kind of thing. We need precise definitions of what are the inputs, what are the outputs, what are the semantics of the task. Then we need label data sets to measure how good are they doing on that task or automation. Input-output pairs to assess the accuracy of the task. And it's not enough just to assess the data prep step. You need to look at, is it really useful for the ML model that the AutoML tool is building at the end? So that's the downstream model. Does it really help downstream predictions? And this is what we set about doing in this project. At a deeper scientific level, more fundamental questions here are, how exactly does data prep affect ML accuracy in terms of the bias variance noise trade-off? Anything that you do to the data is going to potentially affect your bias variance noise trade-off in potentially non-trivial ways. Just like you do with feature engineering, just like you do with algorithm search or hyperparameter tuning. So data prep has to be studied in that context. Once we understand that more deeply, can we build better fail-safes so that these automated tools can account for possible errors and then try to avoid them in their pipelines? So these are sort of longer-term questions also that this work could lead to. So as a starting point, we defined 6 common data prep tasks that we saw happening in various settings and across many of these tools. These are not comprehensive by any means. There's literally dozens, even hundreds of data prep tasks that people need to do, but not all of them are made equal, of course. Some of them are very ubiquitous. And so these are some tasks that we saw as being common. So first one was ML schema inference, identifying from the raw tables, like say structured data is where data prep is very complex. What are the feature types, categorical, numeric, and so on. Once you identify categoricals, you need to deduplicate redundant kind of category representations like California and CA. Anomalous categories, extract numbers from strings, kind of very mundane sounding tasks. But this is where a bulk of data scientists' time goes in today when they're doing ML on structured kind of tabular data. In the Sorting Hat project, we've been building ML models for some of these data preparation tasks and building labeled data sets. And we've also been collaborating with industry in this space. There seems to be a lot of interest among many of these AutoML platform vendors. And we've been collaborating with the TensorFlow data validation team in TFX at Google. And they are interested in our schema inference models for automatically identifying the ML schema. And we've been collaborating with them for about a couple of years now. They've taken our models, they're now benchmarking it on their internal AutoML suite as well. More recently, we've gotten funding from NSF for this new search system that matches data sets and models called AI Maker, where our models will be used as part of the automatic kind of schema extraction and identifying the data sets. And AWS also gave a gift, and they're collaborating with us. Some of their database teams and their ML AI service teams are interested in the schema inference and other aspects of automated data prep. OpenML, which is this community repository for collaborative machine learning, is also interested in some of this for the catalog search, for detecting feature types, and so on. So there's a lot of open questions in the space of automation of data prep for ML. And I believe a lot of these can be interesting to data mining folks as well. So that's to summarize this whole DBfication of ML and AI that I've been talking about. I gave you 2 examples, one from the sourcing stage, one from the model building and deployment stage. There's really a whole slew of open technical questions from the data management standpoint, from the system standpoint, where we need to tackle these in order to help democratize ML AI. If we leave these problems open, that will result in a huge waste of time, user effort, money, and energy because of resource wastage by a huge number of users of ML AI across all sorts of application domains. And tackling these sorts of problems really requires unifying and synthesizing multiple research communities' work. And we need to join forces. And I think the data mining community is also necessary in this sort of endeavor. to be able to democratize ML AI. So that's what I'm going to talk about in the last part of my talk. How do we reignite this sort of nexus between the database community, like talked about the roots of the data mining community lie there. These are not comprehensive lists. Again, this is just a set of prominent examples that I want to give for what I think data mining can bring to the table in the DBfication of ML AI. As I see it, data mining problems are pervasive in this whole life cycle across all stages. For example, in the source stage, we need to have dataset discovery systems on data lakes where people have hundreds of thousands of datasets even in many large organizations. How do we figure out what datasets are most useful for some given prediction task? We need search systems for this, for collaborative kind of data science. And I myself am collaborating with a data mining colleague here at UC San Diego for that AI Maker project that I mentioned earlier. Label engineering is a key bottleneck in many applications where the application itself doesn't naturally provide the label data. To sit and label this, instead of doing it manually, can we do it programmatically? And can we use machine learning itself to auto-generate some labels? This techniques such as weak supervision, distance supervision. Some of this has already been receiving attention in the data mining world. We need to amplify that, help apply that to all sorts of data modalities. Once we have this overarching end-to-end picture of data science pipelines in ML platforms and so on, when a data scientist needs to build some models, instead of starting from scratch, can we build recommendation systems that recommend what to do for the data science pipeline, all the way from data transformations to model building? These sorts of recommendation systems for the whole pipeline could be potentially very useful to kind of improve the productivity of these data scientists. Once a model has been deployed to an application, periodically they need to update it. These days in the online world, in many web companies, they want to do this more automatically so that they could resort to fixing the data or fixing the models to make sure that errors don't happen again. There is some work in the statistics world and in the ML and data mining worlds for kind of detecting concept drifts and so on, but they need something that is more actionable, it's more interpretable for them to act on so that they could improve the ML accuracy in the pipeline. And another example is as automated ML platforms are being built, people are realizing that they still need some human intuition for specifying some search space. So these sort of hybrid human in the loop auto ML platforms that are coming up, we are building one such system on top of Cerebro as well, an interface. Understanding the implications of, say, AutoML search heuristics in that context is another interesting data mining technique, data mining technical question that could be of interest to this community. So all of these are essential as part of the democratization, as part of the DBfication of ML that I'm talking about. Okay, how do you get into this space if you are interested, if all of what I'm talking about has been exciting to you? One thing you can do is check out these courses that are being designed at the intersection of database and ML. So one such course is my database, data systems for ML course at UC San Diego. It's a graduate course that I put a lot of work into. A lot of people around the world have been sending me notes about this. All the materials are available online. Videos are available online. People from industry have also been dropping notes for thanking me for creating this course. I've also been part of a research-oriented textbook, Data Management and ML Systems, that came out a couple of years ago. Feel free to check that out as well. More importantly, it's not just publishing papers in this space. We need to build real software tools and prototypes, preferably open source, collaborate with folks in the database world to kind of flesh out solid software prototypes. We need to also collaborate with other areas, systems, wider systems community, HCI community, programming language community, for various problems across this life cycle. Attend these workshops, the Data Management for End-to-End ML, DEAN, Human in the Loop Data Analytics, HILDA, at the SIGMOD. There's also this new conference, Machine Learning Systems, MLSys, that has been launched in the last few years, where they are kind of pulling together different areas to understand how we build better ML systems. Check out recent tutorials that have targeted this sort of DBfication of ML AI. What are the data management questions? What are the systems questions in how do we democratize ML? There's a few tutorials at SIGMOD and VLDB. There's also an explosion of new research activity. So there's a lot of papers as well, organized into kind of easy to access sessions. There have been panel discussions on this for a long time. I myself have been involved with a couple of panel discussions on this. What does the data management community bring to democratizing ML? One was at the SIGMOD DEAN workshop in 2018. That got a lot of hits and people were excited. And I ran another panel in SIGMOD, at SIGMOD this year. This is the one on data preparation, and this was also a hot button discussion. And I might write a blog post on this pretty soon, so keep an eye out for that. in terms of publications, it's great to see that all these conferences are now kind of focusing on this more. And we are in the applied data science track, right? So KDD has this. I hope it grows. I hope more people want to publish about data management systems issues in this context from the data mining world. The MLSys conference that I already talked about. And at VLDB, I've been part of this new research publication category called Scalable Data Science that was launched last year. And this really helps to kind of publish work that is at the cusp of practical impact, transition from research to practice, that can be from academia, can be from industry, but really aims to help democratize data science. And SIGMOD also has something very similar now. And so now you have all these sorts of top-tier publication venues that you can kind of aim for. Okay, so with kind of that overview, I hope I have convinced at least some of you that the data mining community, I hope, does not settle for being known as just the applied ML or applied AI community. There is a lot that the data mining world can do. There's a key role that they can play in helping democratize ML, AI, and data science. The question really for you all is, are you up for it? That's a wrap. I'd like to thank all my terrific advisees who've been doing all this work. And without them, none of this would be possible. So it's really a privilege to work with such awesome students here at UC San Diego. And with that, I'll end. That's my, again, research group webpage. Feel free to go check it out. All the projects, descriptions, the papers, the videos, code, data sets, blog posts, everything is up on there. Feel free to drop me an email if you want to follow up and connect on any specific projects. And also feel free to follow me on Twitter if you want to get more kind of frequent updates about my research. I'd like to thank all these agencies for funding our research. And I'd like to thank you all for listening to me, and have a great KDD week. Thank you.
Thank you, Arun, for the interesting and informative talk. This was great to hear. Again, for the audience, if you have any questions for Arun, please post them in the chat window. Until we get some questions over there, I will ask the question that I have here in the meantime. Arun, you were talking about joining forces. Can there be more fruitful exchanges in the spaces of DB and systems for ML? And if so, how?
Thank you for having me here, and thank you for the question, Jackie. I hope I'm audible. Yeah, I think there's multiple opportunities for fruitful exchanges. One is, one very impactful one is workshops. Workshops like the team workshop and the Hilda workshop at the DB venues. There's MLSys conference that we could go to. And here at KDD, I'm actually attending the Deep Learning Day tomorrow, which is like a day-long workshop. I'm giving a talk there as well. And that should be entertaining, so you should check it out. I think these sorts of interactions between the different can cross-pollinate some ideas. Another possibility is tutorials. So people from the DB world and the systems world are giving tutorials at these ML venues and vice versa. So how does data preparation work? How does AutoML work? That could be tutorials the data mining folks could kind of reach out and connect with database and systems folks with. And I saw there's some tutorials here at KDD about distributed ML and AutoML systems, scalable ML systems as well. So I think that will also help with the cross-pollination. And the third one could be collaborative research projects. A lot of the folks in this space are collaborative by nature, right? Data mining involves a lot of application areas, so we collaborate with so many application areas. One of the most important application area right now is this DBfication of ML I'm talking about, this platformization of ML. And so data mining collaborate with folks who are building these sorts of platforms of ML, and then I think data mining can contribute a lot to that as well.
Great, thank you very much. I do have another question here for you. Can data mining folks contribute to building of emerging ML platforms, either via user feedback or contributions to parts of capabilities?
Yes, I think so. Absolutely. I think in the data mining world, there's a lot of emphasis on applications that are publishing papers, and then you deploy the model into part of an application. This building a system or building a tool, there is some effort as well. There's like libraries that people have used that are very popular. In terms of contributing to a larger system environment or larger platform environment, I think there are slices of those that can involve contributions from data mining. Like one of the examples I gave was recommendation systems. these tools like MLflow and TensorFlow Extended, they allow you to specify the end-to-end pipeline in a higher level language or higher level API. And so you get visibility into that. And some of these platform vendors actually have traces. They have thousands, tens of thousands of traces from internal users at Google, internal users at Databricks, and even at many enterprise companies. That could be a very interesting data set to learn from for recommending, say, auto-completion or featurization or model building. These sorts of really out there tasks, recommendation systems for data science pipelines could be potentially very impactful. It could also be very impactful in new integrated development environments. Like, for example, we have for data preparation Trifacta. They're already doing this for data preparation. And now SageMaker and all these other ML platforms are coming up. They're trying to lower the barrier to entry for domain users, for people who may not have deep ML expertise. And so these sorts of recommendation systems that use data mining, but data mining applied to data science workflows could be a really nice way for them to plug in these sorts of software contributions. Now, these MLflow and these TFX and all these things are open source. I hope some of these companies are releasing these data sets also in the public domain for people to work with. On GitHub, there's a lot of repositories of notebooks where we can understand what these end-to-end pipelines look like. So there is already that possibility there.
Great. Thank you very much again. Very interesting.